Hi everyone, welcome to 1 by 0. Today I'm going to be talking about the unit circle, and in particular, one way to remember the sines and cosines of the common unit circle angles. Now, if your experience of learning the unit circle was anything like mine was, you were probably just handed a sheet with a bunch of angles and sines and cosines written on it, and just told to memorize it. Now that's what I expressly want to avoid doing today. Instead, I'm going to teach you a method called angle families that will hopefully make the whole circle easier to remember. As a little preview, those families are going to be the 0-degree family, the 30-degree family, the 45-degree family, the 60-degree family, and the 90-degree family. But before I get into any of that, let's start with some fundamentals. The first important concept we're going to need is that on the unit circle, cosine and sine are literally coordinates. Now, to see what I mean by that, let's draw a line from the origin out to any point on the circle, and let's give that point the coordinates x and y. Now, the unit circle by definition has a radius of 1, and this line that we've just drawn is a radius of the circle, so it must have a length of 1. Now, the trick here is going to be to draw a line from our point straight down to the x-axis, and then draw a second line across from there to the origin, so that we end up with a right triangle. This angle in here I'll call theta, and that's the angle between our original line and the x-axis. So that's the angle whose sine and cosine we want to determine. To do so, let's look at this triangle we've just created. This length right here is equal to the vertical distance from our original point down to the x-axis. So by definition, that must be a length of y, whatever the y coordinate is of that point. Similarly, this length here is the horizontal distance from our point to the y-axis. So it must have a length of x, the x coordinate of the point. To calculate cosine of theta then, we know that cosine is adjacent over hypotenuse. So in this case, the adjacent side is x, and the hypotenuse is 1. So simplifying that fraction just gives us x. Similarly, to calculate sine of theta, we do opposite over hypotenuse. In this case, the opposite side is y, and the hypotenuse is still 1, so we end up with y over 1, which is equal to y. So what we end up with is one equation that says x is equal to cosine theta, and another equation that says y is equal to sine of theta. Or in other words, these coordinates x comma y we can instead think of as cosine theta comma sine theta. In summary, the line at angle theta hits the unit circle at the point cosine theta sine theta. How is this useful? Well, let's say we're working with an angle of 30 degrees, and just as an aside, when I write 30 degrees on top of a line like this, I mean that the angle between the line and the positive x-axis is 30 degrees. Since I'll be drawing other lines with other angles, I don't want that region by the x-axis to get too crowded, so I'll just be writing my angles on top of the lines like this. Going back to our trig functions, 30 degrees has a cosine of root 3 over 2 and a sine of 1/2. Meanwhile, 60 degrees has a cosine of 1/2 and a sine of root 3 over 2. So if you're trying to memorize these from scratch, it might be easy to get these mixed up. After all, it's the same numbers being used, and the only difference is which one is the sine and which one is the cosine. So if you think about this visually, we can see that for 30 degrees, the x-coordinate of that point has to be greater than the y-coordinate, which is consistent with the ordering of root 3 over 2 comma 1/2, rather than the other way around. In other words, the visual sense that we get from coordinates tells us that the cosine of 30 degrees has to be greater than the sine of 30 degrees. We could apply the same reasoning to 60 degrees, seeing that the x-coordinate has to be less than the y-coordinate, which tracks with having the order 1/2 comma root 3 over 2. Or, in other words, the cosine of 60 degrees has to be less than the sine of 60 degrees. Now, this coordinate interpretation is useful when you already know the values that you're working with, but I kind of pulled these out of nowhere, so how can we actually remember these values? That brings us to our second important concept, which is that coordinates on the unit circle follow a root n over 2 pattern. To see this, let's fill in the other angles in quadrant 1 here. So you've got 0 degrees, 45 degrees, and 90 degrees, in addition to the 30 and 60 that are already there. And we can go ahead and fill in those cosines and sines, those coordinates, for these 5 angles. So in counterclockwise order, those are going to be 1, 0, root 3 over 2, 1 half, root 2 over 2, root 2 over 2, 1 half, root 3 over 2, and 0, 1. Now, to really see the root n over 2 pattern, it can be helpful to organize these cosines and sines into a table. So let's go ahead and make a table with 3 columns for theta, cos theta, and sine theta, and fill in the values for these different angles. So for 0 degrees, we have the cosine as 1, but I'm going to write that as the square root of 4 over 2, and you'll see why in a moment here. Meanwhile, the sine of 0 is going to be 0, which again I'm going to write a little differently as root 0 over 2. For 30 degrees, we have root 3 over 2, 1 half, and I'm just going to add a little square root on top of that 1 there. For 45 degrees, we have root 2 over 2, root 2 over 2, nothing to change there. For 60 degrees, we're going to have root 1 over 2, root 3 over 2, and for 90 degrees, we have root 0 over 2, root 4 over 2. Now, what do you notice? In the cosine column, we've got this descending pattern of root n over 2, for n going from 4 all the way down to 0, which makes sense, because if we look at the x-coordinates of these different points that we've mapped on the unit circle, the x-coordinate is decreasing as we increase that angle counterclockwise. Meanwhile, in the sine column, we've got the same pattern happening, but going in the opposite direction. You've got an increasing series of root n over 2. And again, this makes sense, because as we increase the angle counterclockwise, the y-coordinate of that point on the unit circle is going to increase. Now, you might be thinking, well, that's all well and good, but what about the other quadrants? We've just been talking about quadrant 1, and there's still 3 more left to cover. Well, that's a fair question, but worry not. We'll be able to cover the other 3 quadrants in one fell swoop. The way we're going to do that is with concept 3. Every unit circle angle belongs to one of 5 angle families. And rather than trying to write out a general definition for an angle family, let's start with a concrete example. We can start by defining the 0 degree family as the set of all angles on the unit circle that are 0 degrees above or below the x-axis. So we end up just having 2 angles in this family, 0 degrees itself and 180 degrees, and the only difference in their trig functions is that the cosine of 0 is positive 1, whereas the cosine of 180 is negative 1. The sines of both these angles are 0, because the y-coordinate of any point on the x-axis has to be 0. Now, to really see the magic of angle families, we're going to want to go up to the 30 degree family. This is the set of all angles on the unit circle that are 30 degrees off of the x-axis. One quick note, we usually treat the positive x-axis as representing 0 degrees, but because 0 and 360 degrees represent the same angle, we can use this value of 360 when calculating angles in the bottom right corner of this graph. Okay, so going back to this angle family, what do we notice about the coordinates? Well, the coordinates in these other 3 quadrants all match the coordinates in the first quadrant, at least numerically. The only difference is the signs. In quadrant 1, we have a positive cosine and a positive sine. In quadrant 2, we have a negative cosine and positive sine. In quadrant 3, we have negative cosine and negative sine. And in quadrant 4, we have positive cosine and negative sine. And that'll be true in general. Quadrant 1 will be positive positive, quadrant 2 will be negative positive, quadrant 3 will be negative negative, and quadrant 4 will be positive negative. So, now that we've seen how the pattern works, we are ready to blaze through the 3 remaining angle families. But don't hesitate to pause the video and let this sink in more if you need a little more time. So, next up is the 45 degree family. These are the 4 angles that are 45 degrees above or below the x-axis. We see that they have this root 2 over 2, root 2 over 2 pattern in their cosines and sines, and positives and negatives assigned according to which quadrant they are in. After that is the 60 degree family. These are all 60 degrees above or below the x-axis. and they follow the pattern of 1/2 root 3 over 2 for their cosine and sine, again with positive or negative according to quadrant. Finally, we have the 90-degree family. These are the two unit circle angles that meet the x-axis at right angles, and since they both sit on the y-axis, they're going to have cosines of 0 and sines of +1 and -1. Alright, so with all of that in mind, let's try putting it into practice. Suppose we are asked to find the sine of 240 degrees. Well, we can start by asking, which quadrant is it in? We know that the boundaries between the quadrants are at 0 degrees, aka 360 degrees, at 90 degrees, 180 degrees, and 270 degrees. We know that our angle of 240 is going to be between 180 and 270, and therefore it must be somewhere in quadrant 3. This is useful not just because it tells us where to draw this angle in the unit circle, but also because, based on its location, we know that its cosine and sine will have to be negative. Next, we can ask which family is it in, or in other words, what is this angle between the x-axis and our angle? To do this, we just need to take the difference between 240 degrees and 180 degrees. That ends up giving us a difference of 60 degrees, so 240 is in the 60-degree family, which tells us that its cosine and sine follow the 1/2 root 3 over 2 pattern. Now, one of these two coordinates is our answer for the sine of 240, but which coordinate is it? Well, remember that the x-coordinate gives us the cosine and the y-coordinate gives us the sine. So, since we are looking for the sine, we simply pick off the y-coordinate to see that the sine of 240 degrees is negative root 3 over 2. So, the general process for finding a trig function of a unit circle angle starts by asking what quadrant is it in, 1, 2, 3, or 4. This will determine the positivity or negativity of the coordinates that we're after. Second, we ask which family is it in, 0 degree, 30 degree, 45 degree, 60 degree, or 90 degree. That will tell us how far off the x-axis our angle is, as well as the numerical values of its cosine and sine. Finally, all that's left to ask is which coordinate is it? Using the relationships x equals cosine and y equals sine, we can pick off the correct coordinate for our final answer. That's all for today. Thank you so much for watching. If you enjoyed this video or found it helpful, I have a few more steps for you. Please give this video a like, go ahead and subscribe to my channel, and if you have any other topics you'd like me to cover in my next video, go ahead and leave a comment. Thanks again, and until next time, this has been 1 by 0.